So, welcome everyone to this session where we'll be quickly discussing a little bit about the problem that was posted on our Instagram channel. By the way, I am myself Arun Kumar Sahu. I am a physics teacher at Shiksha Gurus Academy and also so today we'll be discussing this problem that was posted on our channel. Let me quickly go through the question itself. So it's mentioning that there are three particles ABC, each of masses 1 kg, 1 kg, and 2 kg, are connected by identical. The word elastic is very important here. Identical, elastic, and almost inextensible threads. So the word elastic here will mean there cannot be any loss of energy. So whenever you have an interaction where there is no loss of energy, such interactions can be related to elastic collisions. Okay, next. So the threads are straight and the angle between them is 60 degrees. So you have a thread AB and thread BC, the angle between them is 60 degrees. The ball A is projected with a velocity of 6 meters per second and the connecting thread parallel to the thread connecting B and C. So this means this line here and this velocity are parallel. What is the velocity of C when C begins to move? So they are asking with what velocity will C move? Okay, so for any question in mechanics, it's important to in general first visualize. So the visualization of this problem goes like this. So A will be initially at this left point, and as time will progress, it starts to move rightward. So for a moment of some time, the thread here will be slack here, it will be slack, slack. So till the time the thread again becomes the original length, it will be slack. And when it becomes the original length, this angle, if it is 60 degree, this angle will be 60. So a isosceles triangle is formed here. Okay, so a kind of triangle like this. So you'll have a isosceles triangle. And when the ball reaches here, here this angle is 60 degree. Since these two lengths are equal, this will be 60. So hence it will form a equilateral triangle. So even this angle can be said to be 60 degrees here. So when it reaches this position that is shown in this figure 1, you can say that the ball till then didn't have any force from the thread since it will be slack. So when the ball A reaches here, as soon as it reaches here, the thread begins to now have a small force and slowly that force will, not slowly, rapidly that force will develop. Okay, so just before the forces develop, let us just resolve the velocities. This u will have a component u cos theta and a component u sin theta. So u sin theta won't be affected because this force will be perpendicular to this velocity. So when a very brief moment of time, this velocity will try to pull the thread. So the thread extends and it will quickly pull the mass m1 inwards. So as it is pulled inwards, this will move upwards. So its momentum will just exchange since this will be acting like a elastic collision between A and B. The reason why we say it is elastic is very important. This is because it is almost like the forces that are acting are non-dissipative in nature. The energy is not lost. And also there is a momentum exchange. So during this short interval of time, this is like momentum is getting exchanged in the direction of the thread TS and there is no external force. So we can conserve momentum and also conserve energy. When you do conserve momentum and energy, the situation is also called elastic collision. Okay, now comes the interesting part. So since they have equal mass and the velocities are equal, I mean the velocities of this is u cos theta and this is 0. After the impact or after the interaction, the velocities get exchanged like in a elastic collision of equal masses. So this velocity u cos theta is given to this body m2 and after a moment we'll observe that m1 will have u sin theta left out and m2 will have a velocity of u cos theta. So since they have equal masses, the velocities are first exchanged along the red thread. So this is the red thread. Along this red, the velocities are exchanged and this will have zero velocity. This has u cos theta. Now there will be a elastic collision again between these two masses, the mass M2 and the mass M3. So in this situation, the two masses so the two masses will be again undergoing one more elastic collision. This time, the velocity u cos theta has to be broken into a component along this thread because the interaction will happen along this direction, and use cos theta sine theta component will be perpendicular. That won't be involved in the collision in this direction. So now since the string is again elastic, hence another elastic collision will happen now between these two. So this is pehle approach going with a relative velocity of separation of u cos square theta with respect to this which is not moving. So here we will write external forces in this brief moment is zero. So we can conserve the momentum and write the velocity of separation and approach. That is the equation for E. So one equation is the momentum equation of this. This is before the collision and this after the collision or interaction. So after interaction, we assume M3 moves with V3 and M2 moves with V2. So we will say the final momentum is M3 V3 plus M2 V2, which is shown here. The initial momentum will be M3 times 0 plus M2 times the velocity u cos square theta. So we wrote initial momentum equal to the final momentum along the thread. Now we write the equation for E. And the interesting thing here is that initially they are separating away. So u cos square theta is outward, they are separating away. And later on, after the impact, V3 will become more than V2 and they'll approach each other. Usually in our collision ideas, a particle first will approach and then collide and then separate. So this is kind of an inverse of collision where they'll first separate and then they will approach. And since in the equation of E, the velocity of separation approach ratio is always equal, so any which way it won't matter. So V3 minus V2 will be denominator and the approach velocity is, the separation velocity here is u cos square theta minus 0. And thus approach velocity will be V3 minus V2. So V3 minus V2 will be in the denominator, u cos square theta in the numerator. This ratio is E. So we get one more equation from the coefficient of restitution, one equation from momentum conservation. And when we combine these two, we can add and solve for the velocity V3. So I took the momentum equation, I took the E equation, multiplied it with M2, and then I am adding them. So I add this equation and I'll add this equation. So यहाँ पे M2 V2 कट हो जाएगा and हमारे पास M3 V3 और M2 V3 का M2 V3 का एक टर्म आ जाता है. ऐड कर दो, ऐड करोगे. So when you add, this will become M2 plus M3 times V3 and we have 2M in M2 u cos square theta. So then we divide by M2 plus M3 and put in the values. We get the final answer as 1 meter per second. Now, the most important thing, what are the take-home points of this problem? The take-home points are inextensible elastic ropes can undergo elastic type collision behavior. Okay, that's what we have applied here. When external force is zero, we can conserve linear momentum and the velocity of separation and approach equation can be used even when separation happens first and approach happens later. So this equation can be used even when there is a separation first and then approach next. Also, this equation has to be written along the line along which the forces act. Here in this case, since they are threads, they will act along the thread. So we have written all the equations along the thread. Okay. So I hope you learned a few things here, and I would sincerely ask you to revise if needed. This model is quite important, and thank you for your time. Have a nice day. Thank you. Bye.